Behind every 30-second interaction at an ATM sits a high-stakes coordination between a local mechanical safe and a global banking network. Despite its appearance, the terminal is a constrained edge client. It does not possess financial authority. It is merely an interface for a safety-critical distributed system. The engineering challenge is maintaining absolute transaction correctness when the software must rely on mechanical hardware that can jam and networks that can drop at any millisecond. To function safely, the system enforces two non-negotiable invariants. The first is the prevention of phantom debits, where a customer's balance is reduced for cash they never actually received. The second is the prevention of phantom dispenses, where a machine ejects physical currency without a corresponding deduction recorded in the bank's ledger. These layers are logically separated into the edge layer, the routing plane, and the money plane. Each tier has a strictly defined responsibility. The edge layer handles hardware interactions to request authorization. The routing plane manages the delivery of that request, and only the money plane has the power to decide financial truth. Standard web client architectures are built for speed and high availability, but applying those same principles to a cash dispenser reveals immediate structural flaws in how we handle state and consistency. In many system designs, a bank account is modeled as a simple database row with a mutable balance field. This creates a race condition. If two separate ATM withdrawals hit a single balance cell at the same time, one transaction can overwrite the other. The machine dispenses $600, but the database only records a $300 deduction. To prevent this, banks use a ledger-first architecture. Instead of a single mutable cell, the system maintains an append-only sequence of immutable transaction records. In a ledger system, the account balance is a derived value. It is dynamically calculated by aggregating the history of every successful credit and debit. This provides inherent concurrency safety. Because the system never modifies existing data, simultaneous requests simply result in new, distinct entries on the ledger, providing a mathematically auditable trail. An append-only ledger creates a risk with network retries. If the ATM drops connection and sends a request twice, the ledger might double charge the customer. The solution is an item potency key, or transaction ID, generated at the physical ATM for every withdrawal attempt. The money plane checks this key before writing to the ledger. If it detects a duplicate ID arriving from a retry, it returns the original result rather than creating a second entry. By using an immutable history rather than a mutable snapshot, the system ensures that financial truth is derived from facts, not overwritten states. Security begins by establishing the ATM keypad as a zero-trust boundary. Plain text PIN data must never exist in the machine's memory or the network storage. This uses the Derived Unique Key Per Transaction Protocol, or DUKPT, ensuring every transaction uses a unique encryption key. The process requires a base derivation key, stored in a secure facility, and the device's key serial number to generate a one-time session key. This session key is discarded immediately after use. Even if a network packet is intercepted, the attacker cannot use that key to decrypt past transactions or predict future ones. As the encrypted packet leaves the machine, the ATM must provide a REST authentication token, retrieved through the API/GetToken endpoint, to validate the terminal at the API gateway. The validated packet enters the money plane and reaches a hardware security module, or HSM. This is a tamper-resistant device where the sensitive cryptographic operations actually occur. A common vulnerability in backend systems is a key repurposing attack, where an attacker tricks the HSM into using a highly restricted PIN key to decrypt general data. TR31 key blocks prevent this. They wrap the symmetric key inside a digital envelope with specific usage attributes, like PIN encryption only, stamped directly on the outside. This physically binds the key to its intended purpose. If a request attempts to use a PIN decryption key for general data, the HSM will detect the mismatch and reject the request. In this environment, security is not a network perimeter. It is a mathematical constraint enforced from the physical keypad to the deep backend. To coordinate the hardware and the ledger, the system follows a commit after dispense protocol. Funds are reserved immediately, but the ledger is only permanently debited once physical delivery is confirmed. An explicit state machine manages this process. Every withdrawal starts in the initiated state once the customer selects an amount. The backend transaction processing system places a hold on the ledger, moving the transaction into the funds held state. With the funds securely reserved, the ATM commands its internal cash dispenser mechanism to begin ejecting the physical bills. As the cash moves, internal sensors count the bills to verify the correct amount has passed the exit slot. After the sensors confirm delivery, the ATM sends a confirmation back. The hold converts into a posted debit, moving the state to committed. But what happens if the network drops after the cash is ejected, but before that final confirmation reaches the ledger? Trading this timeout as a failure to immediately reverse the hold is dangerous. If cash dispensed just before the drop, the customer receives free money. To manage this, banks use the saga pattern. It breaks the transaction into a sequence of local steps, allowing for a more resilient approach than traditional database locking protocols. When an ambiguous timeout occurs, the saga shifts the transaction into a needs reconciliation state. Automated reconciliation jobs then cross-reference the central ledger against the ATM's internal device journal to determine exactly what happened during the outage. If the journal proves that the dispenser jammed and no cash was delivered, the system executes a compensating transaction, safely reversing the hold and restoring the customer's funds. In systems where physical assets are at stake, ambiguity must be managed through explicit states and evidence-based reconciliation, never through assumptions. This unified architecture, from HSMs enforcing security to sagas managing physical failure, ensures that the system can recover gracefully from nearly any infrastructure outage. This is a practical application of the CAP theorem. A distributed system must choose between consistency, availability, and partition tolerance. The ATM prioritizes consistency. If it loses connection, it cannot access the ledger, and dispensing cash on a stale balance is rejected. Unlike a social media application that may favor high availability by showing you stale data, a financial system must remain perfectly consistent to be trusted. When a machine cannot reach the backend, it displays this familiar screen. This is not a failure of the software. It is the system successfully defending its core consistency invariant by refusing to process an ambiguous transaction. This level of design anticipates hardware jams, severed network lines, and cryptographic attacks at every single node in the architecture. By accounting for both physical mechanical failure and digital network loss, these systems provide a reliable bridge between the world of perfect code and the reality of imperfect hardware.